Let's now talk about linear and angular speed. All right, so we're going to relate the speed of objects that have circular motion. Consider a particle moving at constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed v of the particle is given by the equation v is equal to s over t. All right, linear speed v is equal to the arc length divided by the time it takes to travel through that arc length. All right, and so this is just distance divided by time. And hopefully you guys all know that's how we find speed. We take the distance that we travel and we divide it by the amount of time that it takes us to travel. In this particular case, because we're dealing with circular motion, the distance that we travel is considered the arc length through which we travel through. Now, moreover, if theta is the angle in radian measure, again, everything should be in radians here, corresponding to the arc length over which the particle has traveled, then the angular speed, omega, this is lowercase omega, the letter that we use to represent angular speed, is given by theta over t. All right, so angular speed. When you see the word angular speed, the key word is angle here. And so instead of a distance divided by time, we are taking the angle which we rotate through and divide it by time, theta over t. Now, again, very, very important that theta is measured in radians here. Okay, so let's do a little bit of manipulation real quick. So we have v, our linear speed, is equal to s over t. Recall that s, the arc length, can be written as r times theta. That was our arc length equation. So let's substitute that in. That means v is equal to r theta divided by t. And theta divided by t, this quantity right here, that's the same thing as r times theta over t. Well, theta over t, as we see just above, is equal to omega, which means that v is equal to r times omega. So the three main equations that you want to take away from this page are this one for linear speed, this one for angular speed, and then this relationship between our linear speed and our angular speed. V is equal to r times omega. So anytime you're looking to find linear speed and you have the angular speed, all you have to do is multiply by r, the radius of the arc, okay? This common manipulation shows the relationship between the linear speed, v, and the angular speed, omega. All right, the second hand of a clock is 15 centimeters long. Find the linear speed of the tip of the second hand as it moves around the face clock. All right, the clock face. All right, here we have our second hand, and we said that it is 15 centimeters long. We are looking to find the linear speed. Well, how do we find linear speed of an object that has circular motion? V is equal to s over t. So we're talking about the arc length per unit time. How long does it take our second hand to make one complete revolution? Well, 60 seconds, right? 60 seconds in 1 minute. It takes 60 seconds to complete one full revolution. All right. And if we are completing one full revolution, what would be the arc length that we travel through? Well, let's think about finding arc length. Arc length, S, is equal to r, the radius of the arc, times the angle which we rotate through. And as we have said before, one full revolution, well, that's 2 pi radians. So we have S, our arc length, is equal to 15 centimeters, r, times 2 pi, our angle theta of one complete revolution. That gives us 30 pi centimeters. All right, so now that we have S, how long does it take us to rotate through that arc length? Well, it takes us 60 seconds. V is equal to S divided by T. We have 30 pi centimeters divided by 60 seconds. That gives us pi over 2 centimeters per second. And if you were to plug that into your calculator to get a decimal approximation, pi over 2 is approximately 1.57 centimeters per second. All right, so that is the linear speed of a point on the outside of the end of this second hand. There's our linear speed. All right, let's look at another problem involving circular motion. Adam and Bailey are riding on a merry-go-round. Adam is sitting on a horse that is located 60 feet from the center of the merry-go-round. Bailey is on a dragon that is located 40 feet from the center of the merry-go-round. The carousel, or merry-go-round, makes 4 revolutions per minute. All right. Again, when in doubt, let's draw it out. So here we have Adam. Adam is 60 feet from the center, and he is traveling around our merry-go-round. And we have Bailey. Bailey is 40 feet from the center of the merry-go-round, and again travels in a circular motion as well. Okay, the carousel makes 4 revolutions per minute. So both of them are attached to the carousel, and that means that both of them are making 4 revolutions per minute. So determine the angular speed of Adam and the angular speed of Bailey. Well, let's think about our equation for angular speed. Omega is equal to theta divided by t. That is the angle we travel through per unit time. Well, in this case, Adam and Bailey travel through the exact same angle per unit time. Therefore, they must have the same angular speed, right? They're both attached to this merry-go-round. They're not going anywhere on it, okay, except in a circular motion along with the merry-go-round. So both of them travel through the same angle. If one of them does a complete revolution, the other one also has to do a complete revolution. This merry-go-round completes 4 revolutions per minute. Well, we have a unit of time and we have revolutions. And what we want to do with this revolutions is change this revolutions to radians, because angular speed is a measure of an angle in radians per unit time. Well, we know that 1 revolution is the equivalent of 2 pi radians, and so we can use that as a conversion factor. We can multiply by 2 pi radians divided by 1 revolution. And again, the reason we're allowed to use these conversion factors is because we're actually multiplying by 1, right? Any value divided by itself is the equivalent of 1. 2 pi radians and 1 revolution, they mean the exact same thing. How do we check to see if we're using the conversion factor correctly? Well, let's look at our units. Notice here, I've got revolutions divided by revolutions. Those will cancel out, leaving us with our desired final unit, radians divided by minutes. So I have 4 revolutions per 1 minute times 2 pi radians divided by 1 revolution. That gives me 8 pi radians per minute. That is the angular speed of Adam and Bailey. All right, now determine the linear speed of Adam and the linear speed of Bailey. Well, v, our linear speed, is equal to s divided by t, the arc through which we travel divided by time. So let's look at our diagram over here. Which one of these people is going to travel through a greater distance? Adam is actually going to travel through a greater distance, all right, a greater arc than Bailey, and therefore Adam's linear speed must be greater because they do it in the same amount of time. Okay, so we have v is equal to s divided by t, and we said earlier on, to calculate arc length, s is equal to r theta. We can replace s with r theta, and theta over t is actually omega, our angular speed. So we have v is equal to r times omega. All right, So to get linear speed, when we've already found the angular speed, all we have to do is multiply by r, right? And so in the previous part of the problem, we found that omega was 8 pi radians per minute. So that means for Adam, his linear speed v is going to be his radius, which is 60 feet, times his angular speed, 8 pi radians per minute. 60 feet times 8 pi, well, that gives me 480 pi feet per minute. All right, and notice if you're thinking about the units, I have feet divided by minutes. If you're wondering where the radians goes, there are actually no units associated with radians. Remember that radians is a ratio, and the units of that ratio cancel out. So no units associated with radian is strictly a numerical value. All right, and then again, if you plug 480 pi into your calculator, you get approximately 1,508. And for Bailey, her linear speed, v is equal to r times omega again. Her radius is 40 feet times 8 pi radians per minute, her angular speed. That gives us 320 pi feet per minute, which is approximately 1,005 feet per minute. Right? There you have your relationship between linear and angular speed.